Alright, so we're continuing from where we left off last time. We are doing 6.2. So again, if you guys want to speak through your audio, please do that. It's much easier for me to approach and answer your questions, so feel free to do that. So we're continuing 6.2. So this is still 6.2 from last time. So we say use the Laplace transform to solve the initial value problem, y double prime minus y prime minus y equals to 0. And we were able to get up to this point where we almost have the setup. Now we just have to plug in the initial conditions. So picking it up from here, plugging in the initial conditions, we have one here, and one here. Let's plug those in. So we have s squared Laplace y minus s times y of 0. Y of 0 is given to be 1, so let's substitute that. Minus y prime of 0, that's 0, minus s times Laplace of y, minus y of 0 is 1, so minus minus plus, that's 1, minus 2 times the Laplace of y equals to 0. Alright, so now that we have finished substituting our initial conditions, now we can go ahead and kind of move things around and try to isolate the term that involves Laplace y. So if I do that, I'm going to move this one to the right side and then this one to the right side, and then everything else will involve Laplace of y. So we have Laplace y times s squared minus s minus 2 is equal to s minus 1. So that's what we get. And then by dividing it through the expression with Laplace y, we have the Laplace transform of y is equal to s minus 1 over s squared minus s minus 2. So that's what we call the Laplace transform of this differential equation. Now you kind of have to set this up and make it into a partial fraction decomposition because you want to match this with the Laplace table that we had from previously. So if you look it up, so I have it right here. Make it big. So there you go. So you see how if you were to take the inverse Laplace transform, what we have doesn't really match any of these. So we're looking at this form right here because we have a function in terms of s, and if you do the inverse, you get the function in terms of t. So we're heading this direction. So that would give us the solution in terms of the t variable. So to match it up, we kind of have to decompose this right-hand side, and we're going to decompose this using the partial fraction decomposition, again using calculus. So using calculus, we have s minus 1 on top, and on the bottom I can factor this quadratic. This would be s minus 2 and s plus 1. So that's the Laplace transform of y. And then if you decompose this, this is just a over s minus 2 plus b over s plus 1. Do you guys remember this from calculus? Yes, no, maybe, a little, yeah? Okay, so the reason I put a on top of s minus 2 because you have a linear on the bottom, so what goes on top is 1 degree less. So if you had a quadratic on the denominator, you'll put a linear factor on top, 1 degree less. So now that I have decomposed my right-hand side, I have to find what are these coefficients, what is a, what is b, and then I can match it up with the table we have on the table. We can match it up with those functions on the table. So more algebra, right? So solve for these coefficients. So we have s minus 1 is equal to a times s plus 1 plus b times s minus 2. So you're kind of like solving a system of equations. So if you have a better way of solving this, if you learn linear algebra, setting up a matrix, you can do it that way too. Whichever way pleases you, use it. But the idea is to find what is A and what is B. So I'm going to go ahead and just use my algebraic skills and find A and B. So if I let S to be -1, so I'm just picking and choosing, that way it'll cut down some of the work. If I let S equal -1, I have -2 is equal to, so the term involving with A will go to 0, so I can solve for B, so that would be B times -3. So I have B is equal to 2/3. So that's kind of nice. And then if I let S to be, let's say 2, because I know the term involving with B will go to 0, so we will have 2 minus 1. So I'm plugging it into this one. So you have 2 minus 1, that's 1, is equal to A times 3. And the second term goes to 0, so therefore we have A is equal to 1/3. So not so bad, right? So what do we have? We have our Laplace transform of y is equal to A, which is 1/3 over s minus 2, plus B, which is 2/3 s plus 1. So this is what we call the Laplace transform of the differential equations. Okay, so if the question asked you find the Laplace transform, you will finish it right here. That will be your answer. But because we're asked to solve it, we have to do the inverse Laplace transform. So be very careful how the questions are worded. So because we're solving, so we want to solve. So hold on. So I'm writing really messy right now. Want to solve, we take Laplace inverse. So that way you have the function in terms of your t variable, not the s variable, okay? So if I do the Laplace inverse on the Laplace transform we have, now we have y is equal to Laplace inverse of 1/3 s minus 2 plus the Laplace inverse of 2/3 s plus 1. And by doing the inverse, here is when you're going to use the table. So use the table. Now if you're given this question on the final, I'm sure he'll provide you the table on the question, okay? Because without the table, you don't want to memorize these Laplace functions. Like, come on. You will be provided with the table if you were to do the inverse. But if you don't, then your answer will just end right here. So from the table, let's check it out. We want to match up which function looks like a constant over s minus 2. So let's revisit. So here's the table. So we're looking at the one that I boxed. Which one looks like a constant over s minus a constant? Right, so this should be the one we're looking at because that's what we have. 1 over s minus a. So all I have to do is write it as 1 over s minus a. So I'm going to pull out the constants. So we have 1/3 times the Laplace inverse of 1 over s minus 2. So a is 2 in this case. And then the second one will also match with the exponential, but I have to pull out the 2/3. So you have the Laplace inverse of 1 over s minus -1. So that kind of like your a, right? So now we know from the table the Laplace trans inverse of 1 over s minus a is e to the at. That's what we know from the table. So therefore our solution is 1/3. So the first one looks like a is 2, so that's e to the 2t plus 2/3 And the second one is also that same form exponential, but a is -1, so that's e to the negative t. And there you go, that's your solution to the initial value problem. Any question on this? Are we good so far? So note the difference between the two answers that I boxed. If the question asks you find the Laplace transform, you will stop where the first box is. You just find the function in terms of s variable. And if the function says to solve, then you continue and do the Laplace inverse and find the solution in terms of the t variable. So that will be the extra step you need to go through if we're looking for the solution. Alright, so I have one more example for us to work on from 6.2, and then we'll say goodbye to chapter 6. So here's a question I typed just before class so that I don't have to write it. So saving some time. So here's a question. Again, this one we're solving, so we're going to do Laplace inverse, but I'll most likely set it up for you so you can do it at home. Well, you are home. You can do it after class or before class or whenever you have time. Just maybe do it. Okay, so I want to know what is the solution to this problem. So let's use the Laplace transform, right? It didn't say use the Laplace transform, so you don't have to use it, but I want to use it, so let's use it, right? So we take the Laplace transform, both sides, so L of y double prime, and because it's linear, I can separate them, so L of y is equal to the Laplace transform of sine of 2t. Okay, so we take the Laplace transform on both sides of this differential equation. Now, what is the Laplace transform of y double prime? So that's something you have to know from memory. Do you guys remember? Okay, so make sure you guys remember that. So that's replacing Laplace transform of y double prime, and then we have L of y is equal to, well, now for the Laplace transform of sine of t, we need the table. So let's go to the table. So here's the table. So now we're looking at the first column. So sine of at is right here. So the Laplace transform of that is right here. So it's a over s squared plus a squared. Okay, so that's something, again, will be given on the table. So in our case, we have our a happens to be 2. So a is equal to 2. So we have, what was the formula? A over s squared plus a squared. So we have a, that's 2 over s squared plus a squared, that's 4. So that's from the table. Now let's do the algebraic work. So this we need to substitute, this we need to substitute because they are the initial conditions. So we have s squared Laplace of y minus s times y of 0. Y of 0 is 2 minus y prime of 0, that's 1, plus Laplace y is equal to 2 over s squared plus 4. And then we want to group the terms with Laplace of y together so we can kind of factor that. So we have Laplace of y times s squared plus 1 is equal to, and then I'm going to move the other terms on the other side. So we have 2 over s squared plus 4 plus 2s plus 1. And then just putting these all together, we have the Laplace transform of y is equal to Um, so if I were to combine these terms on the right side, I would have to put them in common denominators, right, from algebra. So you would get 2s cubed plus s squared plus 8s um, plus 6 all over s squared plus 4, and then divided by s squared plus 1, so that also goes here. So that's what it comes down to. Well, now you kind of have to set up the partial fraction decomposition, so that way you have the form that we want to read off from the table of the Laplace transform. So let me know if you guys have any questions so far. So hopefully I did the algebra right. So just double checking my work. Okay, so how do we decompose this? So if you look carefully, s squared plus 4, it's irreducible quadratic, so it doesn't factor. And then s squared plus 1 is also irreducible, it doesn't factor. So the terms we're going to have it on top of this fraction, when we write the partial fraction decomposition, it's going to be as plus b s squared plus 4 and cs plus d over s squared plus 1. So you get a linear function on top of each of these fractions because the bottom is an irreducible quadratic. So that's again something from calculus. Let me know if you guys have questions. Now the heavy part of this question is actually finding these constants a, b, c, and d. So you would have to kind of go through that. So I'll leave that up to you. But I did go through the computation on my own, and I found, hopefully I didn't make any mistake. So I found, what did I find? Oh, I didn't solve it. Sorry, guys. Oops. Oh. Okay, so I didn't solve this question, but if you continue, you should be able to find A, B, C, and D. And then once you have them, you kind of want to set up the format that we have on the table for the Laplace transform. So the next thing is so you'll figure these out whenever you have time. That's algebra. So you'll have the Laplace transform of y is equal to, and then once you have those values, you kind of separate the fraction. So you have 8 times s over s squared plus 4 plus b over s squared plus 4 plus c over s squared plus 1 plus c times s over d s squared plus 1. And that will be your Laplace transform. So I don't have the coefficients because that's going to require us to spend another good 5 minutes, and we don't have that much time. So I will leave that up to you. But once you have it, just plug them into this partial fraction decomposition, and that will be your Laplace transform. Now, if we want the solution, how do we go about finding the solution? So then we continue, right? What will be the solution equal to? So it looks so, right? So let's match it up. So if you look here, we want to use, so for the first one, you have, so a is a constant, you can pull it out. So when you do the Laplace inverse, pull out the a. So you have the Laplace inverse of s over s squared plus 4. And then for the second ones, I'm also going to pull out these constants, b times the Laplace inverse of 1 over s squared plus 4 plus c times the Laplace inverse of s over s squared plus 1. And the last one you have is d times the Laplace inverse of 1 over s squared plus 1. So we're missing the constants, but you can figure those out after you have done the coefficient, all this work for computation. We can still answer the question. So for the first one, s over s squared plus 4, that looks like this one, right? S over s squared plus 4. 4 you can rewrite as 2 squared. So it looks like this one is a cosine. So a times cosine of, so a is 2, so that's 2t. So that would be this function plus b. Now, so let's take a look at 1 over s squared plus 4. Can you match that with any of the function on this table? Right? It looks like sine, but we kind of have to play around with it. So if you, where's the table? So if you just rewrite, it's gonna look almost like sine, right? So I have a b here, Laplace inverse. So we have s squared plus, let's say 2 squared. But then for it to be sine, we have to have a, right? A is 2 in this case. So I have to have a 2 there. But then if I force a 2 on top, I have to force a 2 on the bottom as well. Do you guys see that? So that will maintain the 1. Do you guys follow? So then it becomes the sine, right? So then this would become sine of 2t times b over 2. And then similarly, you just continue. So the next one, so that looks like cosine. Do you agree? So that would be cosine of 1. So again, going back to the table, we're looking at this one right here. So 1 over 1 square, that's going to give you cosine. No, sorry, it's not cosine. Did we make a mistake? Yeah, it's cosine. Right here. So this would be cosine of 1. So we have c times cosine of 1t plus, now what about the last one? 1 over s squared plus 1. Which one does that look like? That looks like sine, right? Because here you can say a is 1. So this would be d times sine of t. So any questions on this? So do you guys see why I didn't finish the question? It's almost finished until you have the coefficients a, b, c, and d. Then it's complete. So any questions on this problem? So once you find values for a, b, c, and d, we have the solution. Okay, so just keep that in mind. This question is almost complete if we're able to go through the computation of finding a, b, c, and d. So any questions on Laplace transform? Right, are you guys following? Okay. All right. So that's our conclusion for chapter 6. So we finished 6.1 and 6.2. So we'll start with the next section, which is chapter 10. So chapter 10, we're going to do 10.1, 10.2, and 10.4. So we're skipping 10.3, and then we'll do 10.5. So these are the only sections that are remaining to cover. Now 10.1 is very, oh, sorry for the music. That's outside. I don't know if you guys can hear it, but it was very loud. So we're going to study partial differential equations. So we talked about them very briefly in chapter 1 when we had to classify if the differential equation is partial or ordinary. So that's when we talked about them first time. Now we're actually going to talk about them just a little bit more, but not too much, just enough. So this course is mostly in ODEs, not PDEs. So we study very little bit of PDEs. So it's called PDE for partial differential equations, and we're going to talk about Fourier series. So another types of series that we're going to talk about. So let's start with 10.1. 10.1 is very quick and very short. We're not going to spend so much time on it because it's not super important. It's just understanding the difference between an initial value problem and boundary value problems. So 10.1 talks about boundary value problems. So all this time we've been talking about initial value problems where you have, say, so recall we talked about initial value problems. So you have, say, y of alpha equals to some y naught, and then y prime of alpha is equal to some y prime naught. So this is what we call an initial value problem, right? So you prescribe the condition only at one single value for x. Whereas the boundary value problem, you describe or impose the boundary condition on two different x values. So we can impose something like, so boundary value problems are something like, say, y of alpha equals to y naught, and then maybe y prime of beta is equal to y prime naught. So we impose conditions on two x values. So note the difference between an initial value problem and a boundary value problem. So you're looking at a boundary. So suppose this is your x direction. So we're looking at how does the function behave at this x value or the derivative, and how does the function behave on this x value. So we're looking at two different boundary points. So that's what we call a boundary value problem. So let me show you how to do an example with boundary value problems, and then we'll just quickly move on to 10.2. The more of this you will see in 10.5 when we finally solve a partial differential equation. So we'll be solving the heat equation in 10.5. That's when we're going to need boundary value problems. So that's why this is just like a very quick breeze through these type of problems. So I'll still run through one example, that way we at least know what it is, and then we can just do examples with it. So say we want to solve the boundary value problem. So we will abbreviate it with BVP. So suppose you're given y double prime plus 2y equals to 0. And the boundary condition y of 0 is 1. So at one end of the boundary is 1. And on the other end of the boundary, say at pi, it's going to be 0. So this is a boundary value problem because you're looking at x equals 0, and x equals pi. So two different boundaries. Well, how do we solve it? So just like we did for initial value problems, you write out the characteristic equation, find its roots, write out the solution using one of the roots, and then solve for C1 and C2. Same idea applies here. So if we go ahead and solve this, we write out its characteristic polynomial, which is r squared plus 2 equals to 0. So we have r is equal to plus and minus square root of 2. 2i, right? Complex. Yeah, complex root. So that means our solution to this problem is going to be y of x, which is equal to c1 cosine of square root of 2x plus c2 sine of square root of 2x. Well, now that we have our general solution, now we start plugging in our boundary conditions. So the first boundary condition we have is y of 0 equals 1. So if I plug that in, I have 1 is equal to, so x is equal to 0. Sine of 0 is 0, so the second term will disappear. And cosine of 0 is 1, so c1 is 1. Now let's impose the second condition. So if I impose the second condition, that's also on y. So y of pi is equal to 0. So we have 0 is equal to, so since c1 is 1, I can plug in 1 equals c1, 1 times cosine of square root of 2 pi plus c2 sine of square root of 2 pi. And then my goal is to solve for the constant c2. So we have c2 is equal to negative cosine of square root of 2 pi over sine of square root of 2 pi. And we know because they have same argument, you can use another trig function to rewrite this. Cosine over sine is just cotangent, square root of 2 pi. Keep the argument. So we see that C2 happens to be this constant right here. So we have our general solution to this. So our solution is going to be C1, which is 1, cosine of square root of 2x plus C2, well, C2 is negative, cotangent of square root of 2 pi times sine of square root of 2x. So that will be our solution to this boundary value problem. Any questions on this problem? Does it make sense, guys? Alright, so treat them just like you've been treating initial value problems, except now you're looking at two different boundary values. So that's the only difference with these questions. So everything that we learned, undetermined coefficients, variation of parameters, all of that will still apply for boundary value problems if it's non-homogeneous. So you'll have some homework problem, I think, on web work. If you don't, then just do the ones in the textbook. They're pretty good. Alright, so that will be the conclusion on 10.1. So not really much. It's very quick, just understanding the idea of boundary value problems. So moving on to 10.2. So I'm going to do 10.2 and 10.4 together because it's really good to see both sections done together. I think it gives a really good structure of understanding how this Fourier series works. So 10.2 is Fourier series, and 10.4 is odd and even functions. So 10.2 we will talk about what are Fourier series, how do we compute Fourier series for any given function, and 10.4 we'll talk about specifically how do we simplify these formulas for Fourier series if the function happens to be odd or even. And you'll see how it works really nice when the functions are even or odd. If it's neither, then oops, we don't have any shortcuts for neither functions. But for odd or even, we have some shortcuts. So that's why I'm just going to put them both together. So let's focus on what is a Fourier series. Have you guys heard of this term before in any of your courses? Probably, probably not. No, okay. All right, thank you for sharing that. So let's start. So Fourier series, they're just another way of representing functions, very specific functions, and they're very wonderful. So Fourier series is another way of saying trigonometric series. So just like we had power series for polynomials, now we have series that involves sine and cosine, so trig series. So I like to call them sine and cosine series. So now you can imagine how wonderful they are when you actually graph them. When you graph this function after you have this Fourier expansion of a given function, you'll see how nice it looks. So let me just explain to you again briefly what is the idea behind using Fourier series for any given function. So suppose you have, so here's a scenario. So suppose you have a graph that looks like this. So not pretty at all. So I always have a hard time drawing a straight line, so this is not straight at all. So it's maybe the direction I'm sitting, and my laptop is kind of tilted, so every time I write kind of going upward direction. So it's not straight. Yeah, my fault. Okay, well, it's not a big deal. So suppose you have a graph that looks like this, like a box. Not a box, but kind of like a weird looking wave. Something like that. So it's a weird looking continuous graph, and then it just repeats, okay? Now, what the Fourier series will do, it will compute few coefficients using a specific formula, which I'll give it to you in a few seconds. It will create this nice smooth curve that will best approximate this weird looking curve that we have. So what the Fourier series would do, it will create this very nice smooth curve through this picture so that your function is smooth and continuous everywhere on the entire real line. So the red represents the Fourier series. So that's the idea. If you have any broken pieces, as long as the function is periodic, you can represent it as a sine or cosine function or both, and then the picture would be a very smooth, nice function, very closely approximated to the original given function. That's the idea behind Fourier series. And there's tons of illustration in our textbook that you can look at. My drawing is not the best drawing, but the textbook has wonderful pictures that you can look at and stare at them and just say, wow. Okay, so I'll leave that wow to you so you can kind of enjoy yourself later. But for now, let's write down the definition. What is a Fourier series? So definitions are important. So, definition. So suppose f of x is a 2L periodic function, which means f of x plus 2L is f of x. So every period of 2L, it's going to recycle itself. So we're looking at the period of, let's say, period on. So we're looking at a symmetric interval, negative L to L. Okay? Then the Fourier series representation of the function of f of x is given by the formula. So you have f of x is equal to a0 over 2 plus the infinite sum starting at n equals 1 to infinity of an cosine of n pi x over L plus bn sine of n pi x over L, where the coefficients are a0, an, and bn are given by the following. So you have a0. So I will explain why do we have a a0 over 2 on the formula in a few minutes. I'll give you the derivation as well. So without derivation, these formulas are they're just useful, but then if you don't know the math behind it, it's kind of like, okay, right? Hard to be very convincing arguments, but I'll show you a tiny proof on all of these. So that way you're not just given the formula, you're also given the explanation as well. So a0 is given by the formula 1 over L integral from negative L to L f of x dx, and an is given by the formula 1 over L integral from negative L to L f of x times cosine of n pi x over L dx, and then bn, so the last coefficient, bn is given by the formula 1 over L integral from negative L to L f of x times sine of n pi x over L dx. Very important, so make sure you know all of these. So you don't have to know how to write it out formally, but know that the Fourier series representation of any function is given by this formula. And the coefficients, we can find them by the following formulas. So these two boxes are very important for this section. So now let me give you a derivation where these formulas are coming from. Okay, why is it a0 happen to be that weird looking integral? Why is an equal to that and bn is equal to that? Okay, but before I do that, let me just give you a brief explanation on why is it cosine of n pi x over L. Okay, so we're using period to be 2L. So if you recall from your experience from pre-calculus, where you study a bunch of trig functions, you learn how to graph them. You probably know them by heart by now, hopefully. That should be the case, like you know them by heart. So if you're, yeah, Greg? Yep. All right, hello, hello, hello. Can you guys hear me? Better? Okay, no problem. Thank you, guys. So let's recall from the past. So we know sine and cosine are periodic, right? So their period, so let's recall. So if you look at any sine function, you have sine kx, right? So I'm just looking in a general form. So the period of these functions is 2 pi periodic. So we know the period is 2 pi over k. So that's from the past in pre-calculus. So what we're doing here, we want the interval to be symmetric. So we want to look at negative L to L. L could be any real number. So we want it to be 2L periodic. So if we want the period to be 2L, so we have 2L, which is P, is equal to 2 pi over K. Well, now the question is to solve for K. So if I solve for K, I have 2 pi over 2L. So K is equal to pi over L. Now because sine of 1 pi over L, I have a value, then I can do sine of 2 pi over L, sine of 3 pi over L, 4 pi over L, and so on. So you can let this be, let the period be n multiple integer of pi over L. So that's when you will get all the solutions, right, as we think of for any trig function. So that's where this inside right here, we have K value happens to be n pi over L times x, and then we have sine n pi x over L. So that's where this unknown weird looking variables are coming from. So that's just one illustration to just convince you where these things are coming from. Now the next thing I want to convince you, or at least show it to you, why do we have A0 equals to that formula AN and Bn? Okay, so that would be the next illustration. But before I do that, we kind of have to remember some properties of functions, and there's also something called inner product, which you probably have seen it in one of your calculus course, the dot product. Do you guys remember that? Yeah, right, it rings a bell a little. Okay, so hopefully you remember those concepts, and we're trying to apply that to here. So I did copy some notes from the textbook. So here are, let's see, is this useful? Not yet. So, okay, that's the table. Alright, so we're going to hold on to that. So we're going to come back to that. But before I do that, I want to show you the inner product property. So the inner product property. Or you might have also seen it as dot product in calculus. So just to quickly review, if you take dot product of two vectors, and if the dot product is equal to 0, what do you know about the two vectors? Right, so we know that from calculus, to show two vectors are perpendicular, or in calculus we use the word orthogonal, that means the dot product is 0. So that's the property we want to use, but not for vectors, for functions, okay? So let f and g be functions. Okay, so we want to say that, so this is a claim, the inner product, so you write them like this, the inner product of f and g, which is in an integral form, alpha to beta, so you integrate over a finite interval, f and g, so the inner product of f and g dx. So that's how we represent inner product of two functions as an integral. So we say that f and g are orthogonal if, so they're orthogonal on the finite interval. So on the interval alpha to x to beta, if their inner product or dot product, same thing, is 0. Okay, so that's the idea you want to kind of think of when we try to simplify or derive these formulas in the future. So here's something I want to tell you. Sine and cosine, they're orthogonal to each other. So if you were to integrate sine and cosine over a finite interval, the results will be 0. Okay, so you can verify that for yourself, that sine and cosine are orthogonal functions. So that's going to be very useful on this concept. So let's show one of the formula. So we know f of x is equal to a0 over 2 plus the sum n from 1 to infinity an cosine of n pi x over L plus the sum, so I'm splitting up the sum, n equals 1 to infinity bn sine of n pi x over L. So that's the formula we have. So what are we going to do? First, I'm going to go ahead and integrate this formula respect to x from the symmetric interval negative L to L. So I'm going to go ahead and do that. So let's integrate both sides, negative L to L. So integrate the left side, negative L to L, respect to x. Integrate this one, negative L to L, dx. And then we're going to integrate this one, and then this one. Okay, so of course I'm leaving a lot of details, right? So just bear with me for now. So now what happens if you look at this function sine and cosine, right? I'm integrating cosine of some argument, n pi x over L. That's just an argument. And you're summing over n equals 1, 2, 3, 4, 5, 6, all the way up to infinity. So just focus on one of them. So say n is equal to 1, okay? So back of your head, you should be thinking, okay, so you're integrating negative L to L of an cosine of, so let n be 1, okay? So you're integrating pi x over L dx. Well, what is this integral? What is cosine of pi x over L from negative L to L? Do you guys know what this integral is? What's the integral of cosine? Sine, right? So even if you don't remember by memory, you can go ahead and integrate. So I'll show you this one, and then the second one I'll just generalize it. So we know this is, so leave the an alone. So you have sine of n pi x over L times L over n pi, that's a constant, and you're taking it from negative L to L. So now let's plug in L for x. So you have L over n pi times sine of, so if I plug in the upper limit, I have sine of n pi minus sine of the bottom limit, negative n pi. So what is sine of n pi? Well, again, you're letting, oh, I'm choosing n to be 1. So let's just pick n to be 1. So that's just pi. So again, you can use n pi, but let's just keep it simple. So what is sine of, so that's pi over L, so this is pi, and this is pi x, x is L, so that's pi L, so that's just pi, so sine of pi. So we're looking at sine of pi in this one, and this one we're looking at sine of negative pi. So again, I'm using n equals 1, so n equals 1. What is sine of pi? What is sine of negative pi? That's also 0. So you can see that this integral is 0. So 0 times an will go to 0. So this entire piece go to 0. So even if you do n pi l, for every integer multiple of n, it will still go to 0. So that entire piece goes to 0. Now what about the second piece when you're integrating sine n pi x over L on the interval negative L to L? So do you agree that that will also go to 0? So if you want to check, you can show that this integral will also go to 0. Same idea, integrate sign, choose n to be 1, and just keep going, plug in the upper limit, bottom limit. Eventually you'll see you'll go to 0. So these two integral drops. Well, what are we left with? So we're left with the integral from negative L to L, f of x dx is equal to in a0 over 2 times the integral negative L to L of 1 dx, because everything else was 0. Now, what is this integral right here? What is the value of that? So if you integrate one respect to x, that's x, right? And then if you plug in the upper limit, L, and then lower limit minus negative L, so you have 2L. So all of this will come down to a0 over 2 times 2L. And then on the left-hand side, we have the integral of negative L to L of f of x. So now we can successfully solve for a0. So you see that a0 will simply be 1 over L, the integral from negative L to L, f of x dx. So that's why we have this as the formula for a0 previously in the definition. Does this make sense? Do you guys follow? Okay. So we have shown a0, where that came from. Now let's do another one. Let's do an, and then you'll check bn on your own, why that's the formula. So to show that's the formula for an, what we're going to do, we will start with Fourier Series definition, and then we'll do the following. So let's write it out. So now we're going to solve for an. So we know f of x is equal to a0 over 2 plus the sum n equals 1 to infinity an cosine of n pi x over L plus the sum starting at n equals 1 to infinity bn sine of n pi x over L. And now here's what we're going to do. We are going to multiply this entire equation by cosine of m pi x over L and integrate over that symmetric interval negative L to L. So that's the magic. Well, that's not the magic, but that's the key to this. Okay, so let's do that. So I'm going to go ahead and multiply both sides of this by cosine, so we have f of x times cosine of m pi x over L. So I'm using a different argument. Instead of n, I'm using m, equals a0 over 2 times cosine of m pi x over L, and then plus the sum from an cosine of n pi x over L, n equals 1 to infinity, and I'm multiplying it with cosine of m pi x over L. And the second one, we're also going to put the sum n equals 1 to infinity of bn sine of n pi x over L, and we're multiplying it with cosine of m pi x over L. Okay, so that's done successfully. Well, now we integrate left to right on the symmetric interval negative L to L. So integrate negative L to L dx, integrate negative L to L dx, and integrate negative L to L dx, and integrate negative L to L dx. Okay, so we have done that. Well, here we're going to borrow the inner product property, okay? So, but you have to be very careful how we use this. So let's check this out, right? So we said that cosine on a symmetric interval is equal to 0. We've proven that right here when we're solving for a 0. Cosine of any argument on a symmetric interval negative L to L is equal to 0. So I'm going to use that fact to simplify this a little bit more. So which integral goes to 0? Can you spot that? So do you guys agree that this will go to 0? Because you're integrating cosine on a symmetric interval. Do you guys agree? Yep, okay. And then, so let's hold on to the second one. Now let's look at the last one. You have a combination of sine and cosine. So again, using the inner product property right here, we said that two functions are orthogonal on a finite interval if their inner product is 0. So we know sine and cosine, they're orthogonal. So that means, so this is something you have to verify on your own. So this is by orthogonality of sine and cosine, that when you integrate sine times cosine on a symmetric interval, this is also going to be 0. So this also goes to 0. So you have to justify that. That's for you to check. And now we're left with the one in the middle, okay? So we're integrating on negative L to L cosine of n pi x over L and cosine of n pi x over L. Now check this out. Again, there's a lot of clarification that you need to fill in. We only have just enough time to go through the examples and few computation. So check this out. If I'm going to break this into two cases, cosine of n and m. So if m and n are equal, meaning if the arguments are equal, then the integral of this would look something I'll show you in a few seconds. But if they're not equal, then they're orthogonal, so it's going to be 0. So if m is not equal to n, then that entire integral will go to 0. But if they're equal, then what you're really integrating is this. So you're integrating negative L to L cosine of n pi x over L and cosine of n pi x over L dx, which means I can multiply them, so because they have same argument now, so that would just be negative L to L of cosine square of n pi x over L dx. So that's how you would be integrating this integral if m and n are equal. Now, just to simplify things, again, we're going to let n run from 1, 2, 3, 4, and so on, because that's what the summation is for, right? So what if I pick n to be 1, 2, 3, and so on, right? So we know m is fixed. M is n, so now we're letting n run from every integer, starting from 1. So if I just simplify that, this is the integral from negative L to L cosine square of pi x over L dx. How do you integrate this? So that's something you should have done in calculus. What formula do you use to integrate this? Any suggestions, guys? So if you remember from the past, if you had cosine square theta, right? How did you integrate that? what was the formula that you guys used? Yeah, so you had 1/2 1 minus cosine of 2 theta. Something like that, right? So that's the idea we're going to use here because it's a cosine square. So we can write this as the integral from negative L to L of 1/2 1 minus cosine of 2 times pi x over L dx. And then you just integrate that and evaluate from negative L to L. And you'll see, so again, that's up to you to verify. So these are more calculus question for you to go through. So if you do that, this integral will simply be just L. It's going to come down to L, so trust me. You'll see it if you work through this problem, so you can finish this later when you have time. That integral will just be L. So what do we have so far? So we have on the left side the integral from negative L to L. So let me write it out here too. So this is L. So if m and n are equal, meaning the arguments are equal, then that integral is L. If m and n are not equal, then that integral will also go to 0. Again, you can verify all of these just simply doing integrations. So what do we have? We have the integral from negative L to L, f of x times cosine of m. So I'm letting m and n to be equal, so I'm going to write n pi x over L dx is equal to, so we're left with only the second piece, and I'm writing out the summation as n equals 1, 2, 3, and so on, instead of using the sum notation. So we have an times L, because that's what the integral was, for every n equals 1, 2, 3, and so on. So then by solving for an, we finally have the formula we want. An, it's going to be 1 over L, the integral from negative L to L, f of x times cosine of n pi x over L. So that's the formula we were after. Any questions on this derivation? Okay, so that's the derivation for an. So we were able to do a0 and an. bn, I'll leave that up to you. But the idea for bn would be to, again, take the definition, and now you're going to multiply the definition with sine of m pi x over L. So instead of cosine, just like we did for an, for bn, you would multiply by sine of m pi x over L, and then integrate all sides on a symmetric interval negative L to L respect to dx, and then you'll see most of the term will go to 0 because of the orthogonality property, and at the end you'll be left with something really nice, which will simply write down the formula for bn to be this formula we have. So I'll leave that up to you to verify. Any questions so far? Are you guys okay? All right, no response. Um, okay, that's good. All right, so let me do an example. At least the example wouldn't be a lot of leaving it up to you. So here I had to leave a lot of things up to you because I think they're just simple integration that you can do them just by taking some time off and really work through these examples, okay? Let me do an example so that way at least you know how to use this formula. So here's an example. So we want to do, so let's do this one. Let f of x be equal to the function 2 on the interval 0 to x, x to 1, and then it's going to be 0 on the interval -1 to 0. Let's find its Fourier series. Okay. So let's draw the picture and determine the value for L. Okay, so I'm going to go ahead and draw this function. And then we can extend it as a odd or even function. So it doesn't really say what kind of function, so we're just going to replicate the same function. So we have from -1 to 0, the function is 0. So we have right here the 0 function. And then from 0 to 1, you have the function 2. So it looks something like this. So this is 1 period, right? So this is 2L. So what is L then? So if 2L is from -1 to 1, what is L, guys? 1, right? So L is 1. It's half of the period, right? So L is half of the period. Okay, so we have L. So what is the Fourier function going to do? Well, it will take this periodic function and just replicate on the left side and on the right side, and then create this wave and make it really nice and smooth. So I'm going to replicate 2L on the left side and on the right side. So at least we have a graph that looks similar to what we have. So it's going to go from here to here, 0. So I should use different color. So check this out. So we have from here to here, this is 0, and then from here to here, that's 2. So I'm just replicating some pictures, this picture for more periods. So we have 1 period, we're going to extend it to more periods of this. So we have another one on this side, so that's -2, and then just repeat. So that's the picture if you just extend it for a couple more periods. So I extended to 3 periods. Now what the Fourier series will do, it's going to create this function that's just going to look like this and make everything connected and nice and smooth and so on. So the purple will represent the Fourier representation of this given f of x. So to find this purple graph, we have to compute its coefficients, a0, an, and bn. So let's do that. So a0, we said by definition, it's going to be 1 over L integral from -L to L f of x dx. That was the definition of a0. This function is defined on -1 to 1, but on the interval -1 to 0, it is 0. So if you integrate 0, it's just nothing. So we can integrate from 0 to 1. L is 1, so we have 1 over 1. Integrate from 0 to 1, f of x, which is 2, dx. So this would just be 1 times 2. So a0 is 2. Now let's compute the other coefficients. What is an? An is 1 over L, integrate from -L to L, f of x times dx. L is 1, so we have 1 times the integral. Again, oh, sorry. I think I just miswrote my definition. Oh. What do we have? We have cosine of n pi x over L. L is 1 dx. So then plug in f of x. F of x is 2 on the interval 0 to 1. So we have 0 to 1, f of x is 2 times cosine of n pi x dx. So what we're really doing is integrating cosine. So what is the integral of cosine? Positive, good. So we have 2 times, and then the argument is n pi x, so we have 2 over n pi sine of n pi x, taking it from 0 to 1. So now we plug in the endpoints, 1 and 0, so we have 2 over n pi times sine of n pi minus sine of 0. Well, what is sine of n pi? So you can let n run from 1, 2, 3, right? So what is sine of n pi? What is sine at every integer multiple of pi? 0. So this goes to 0, and we know sine of 0 is also 0. So an is really 0. So this coefficient doesn't survive. Okay, that's nice, right? Simplifies the formula. Let's go for Bn. Bn is given by the formula 1 over L integral from negative L to L f of x sine of n pi x over L. L is 1 and dx. So L. So 1 over L. L is 1. So we have 1 times the integral 0 to 1. F of x is 2 times sine of n pi x because L is 1. Now we integrate sine of n pi x over L. Again, n and pi, they're just integers, real numbers. So what is the integral of sine? So we have negative cosine of n pi x over n pi, and we're going to take it from 0 to 1. Okay, now let's plug in the endpoints. So we have negative 2 over n pi. If I plug in 1, so I have cosine of n pi minus cosine of 0. So cosine of n pi, okay, so we can simplify that. So we're letting n to be every integer, right? 1, 2, and 3, so on. So let's simplify that. So check this out, guys. So if n is 1, we are right here. We're looking at pi. What is cosine of pi? So negative 1, right? And then what is cosine of 2 pi? Right. And then what's cosine of 3 pi? Yeah, right? So you see how cosines keep jumping between negative 1, positive 1, negative 1, positive 1. It's just going to keep jumping, right? Move up and down, 1, negative 1. So we can generalize this because it's always going to be 1 for every odd multiple of pi, and it's 1 for every even multiple of pi. So what we can do is cosine of n pi, it's simply be negative 1 to the n power. So check this out. If n is even, it's going to be positive 1. If n is odd, it's going to be negative 1. So it works. So what are we going to do? We're going to simplify this. So this is equal to negative 2 over n pi. So cosine of n pi is just negative 1 to the n. We were able to simplify that. Minus cosine of 0. Well, we know cosine of 0 is 1. So that's minus 1. And then if I simplify this formula just a little bit more, we have, what do we have? We have, so I'm going to push the negative inside. So this is negative 2 over n pi times negative 1 to the n plus 2 over n pi. So I just distributed that so that it looks a bit simpler. And now this is our Bn. So that's Bn. So An didn't survive, Bn survived, and A0 also survived, right? A0 was 2. So we're ready to write out the solution. So our solution to this, so the Fourier function for this given piecewise is A0 over 2 plus the sum. So remember, An went to 0. So we only have Bn sine of n pi x over L. Let's plug those in. So the Fourier series for this f of x is A0, which happened to be 2 in this case, right? That's right there. So we have 2 over 2, that's 1, plus the sum starting at n equals 1 to infinity of Bn. So Bn is this formula we found, which happens to be negative 2 over n pi times negative 1 to the n plus 2 over n pi times sine of n pi x over L. L is 1, so I'll just write n pi x. So that's the Fourier series representation for this given problem. And now if you write out more terms by expanding this summation, say 2 terms or 3 terms or 6 terms, as many terms you want, you'll see the approximation to this graph is going to be very closer to the one we have. Any questions? So any questions on the computation we just did? Okay, all right. So if there are no questions, someone want to say something? Okay, I guess no. All right. So moving on. Now there's a little bit more to this. Okay, so I didn't simplify the answer completely. There's more I can do with this. If you see this formula that the coefficient for Bn, right, it can simplify a little bit more. Check this out. What happens if n is even? What happens if n is even? What do you get? So pick n to be 2. 0, right? So if you notice, if n is even, we're just summing up 0, a lot of zeros. So we don't want that. So we know Bn is going to go to 0 if n is even. If n is odd, what happens to this coefficient? So we can simplify, right? If n is odd, we have negative 1 times negative 2. That's positive 2 over n pi plus 2 over n pi, which simply be 4 over n pi. So you see how we just simplified a lot by getting rid of all the even powers for n. So our solution actually simplifies more. Our Fourier representation is simply going to be 1 plus the sum starting at n equals 1 to infinity, but specifically for odd integers of n. Okay, so n is odd, and our Bn is going to be 4 over n pi times sine of n pi x. So that would be a simplified answer to this problem. And there is a way to represent odd powers. So there is a rule for odd numbers and there is a rule for even numbers. Even numbers are represented by 2 times n, right? 2 times n will always give you an even number. But odd number, do you guys know the rule for odd numbers? Yep. So you can do 2n minus 1 or 2n plus 1, but if you start at n equals 1, then you would use 2n minus 1. So that's gonna be the rule we'll substitute into our summation, because we want to indicate only the odd integers. So therefore, I can simplify this more. We will have f of x is equal to 1 plus the sum n equals 1 to infinity 4 over n. Well, n is odd, so we're going to use the odd rule. 2n minus 1 times pi times sine of n, which is 2n minus 1 pi x. And that would be your final answer. So any questions on this? So if something simplifies further, you should simplify it completely. Okay. Alright, so that was one example on a Fourier series, just to give you a brief understanding of how to use this formula. Again, most of it just comes down to integration, because if you look at the definition of the Fourier series, it's just this infinite sum starting at n equals 1 to infinity, but you have to find these coefficients by integrating such function, which is f of x. Okay, so it boils down to a lot of integration for this section. Now, I do want to give you a little bit more info before I start giving you more examples. So let's cut down some of the work for computing these coefficients. So here you want to use some properties from odd and even functions. Okay, so that's what I have right here. So I have few properties that were stated in the textbook, and I thought they were very useful for us to use them here. So I'm just gonna, so these are called elementary properties. So they are from elementary calculus, that's why. So I'm just gonna copy them, so just give me a few seconds. Okay, so here's number 4, and there's one more. So these you should have already seen sometime in the past when you took calculus, probably. I'm not sure which course, but you should have seen it somewhere. They shouldn't be super new. They should be like review. So let's check this out. So the first property says if you have a sum or difference of two even functions, the result is an even function. Do you guys agree? This is true? Yes? Is this true? So come up with an example that will help you to remember them. So say you want to look at the example. So sum or difference or quotient and product of two even functions. So x squared plus x squared. Two even function, what is the result? You get 2x squared, even function, right? And then if I were to multiply them, x squared times x squared, I get x to the 4th, which is again an even function. So always think of an example when there is a property that you want to kind of remember for the future reference. And then if you have sum or difference of two odd functions or the product or quotient for odd functions, then the result is even. Oh, right? Let's check it out. So the sum and difference of two odd functions is odd. So take this as an example. If I have x cubed, that's an odd function. If I add x to the 5th, well, sorry, what am I doing? X to the 3rd, right? That's an odd. If I add them up, I get an odd function. So this would be x to the 3rd, right? That's an odd function. Now what if you multiply them or divide them? If you have x cubed over x cubed, let's just keep same function. When you divide them, you get 1. Okay, weird. But you could think it's an even function, right? Now, what about sum? And so the third property, sum or difference of an odd function and even function is neither. So for number 3, we're looking at an example, something like if you have an even function and you want to add an odd function to it. The result is it's really neither, right? You can't really do anything to combine these functions, so it's neither. So hopefully you guys have seen these somewhere in your algebra course. If you haven't, there it is. Number 4 is really coming from calculus. If f is an even function, then if you integrate that even function over a symmetric interval, you can double the integral and take it from 0 to L. Have you guys seen this somewhere? Yes? No? Okay. All right, that's honest. Thank you. So here's something to remember, Suman. If f is even, so if you're looking at any even function, you can double the integral and just go from 0 to L. A quick example to remember this is if you're integrating, say, cosine. Cosine is an even function, right? So if you're integrating negative L to L of cosine of x dx, you can do 2 times the integral from 0 to L of cosine of x dx. So that once you evaluate this integral from the lower limit and the upper limit, you don't have to worry about a negative value. You can just go from 0 to whatever the L value is. It just makes your computation a lot quicker and faster. So we're going to need these when we compute the Fourier coefficient, because sometimes the function you're given might be an even function or an odd function. And sometimes what we're going to do is we're going to extend this 2L period to an odd periodic function or an even periodic function. So that's where we're going to need this for the future reference. And then the last one we have is if you're looking at a function that is odd, so f of x is odd, think of your favorite odd function, sine. I like sine of x, so why not, right? You can think of whichever pleases you, whichever you like. So if you integrate that over a symmetric interval, the result is 0. So if you do negative L to L of sine of x, sine is an odd function, this is going to be 0. Now, how do you know if a function is odd or even? There is a rule, right? There's a way to verify them. So here's a rule. If you haven't seen it, maybe you'll be able to recall. So even function. So a function f of x is even if f of negative x is f of x. So that's the rule to test if the function is even. And for odd functions, so these are sort of like the definition. For odd functions, we have, so a function f of x is odd function if f of negative x is negative f of x. So these are the two definitions we have for odd and even functions. A quick way to check if your function is even or not odd. Now, how do you do it graphically? How do you show graphically if a function is even or odd? Do you guys remember that at least? Yep, absolutely. Thank you. So graphically, if you have an even function, so if you're looking at this picture, whatever that function is, it's even if you reflect it over the x-axis, sorry, the y-axis is just a symmetric picture. So you have something like this. So it's symmetric about the y-axis. So this is an even function. And what about odd function? How do you draw a picture of an odd function? Mm-hmm. So about the line y equals x. No, that'll be inverse function, right? So almost, you almost have it. So I want an odd function for this picture I have. So if you plug in f of x, a negative x, you get a negative f of x. So what it does, it rotates 180 degree. That's where the graph would do. So another way to think of is a reflection about the origin. Okay, so if you reflect this, so that's an odd function. So that's a picture of an odd function. This is a picture of an even function. So even functions are symmetric about the y-axis, and odd functions are a reflection about the origin or rotation of 180 degree. So that's how you can think of odd and even function graphically. Any questions on this? So now, how do we connect this to Fourier series? Well, let's check this out, right? So for Fourier series, so if f of x is odd, right? If f of x is odd, what happened to a0? a0 is, by definition, is 1 over L integral from negative L to L f of x dx. So if f of x is odd, what happens to a0? What can we say about a0? So guys, I'll let you go just in 1 minute, sorry. 1 minute, I'm gonna let you go. 0, yeah, right? By the odd and even function, you can simplify. So we know if you're looking at an odd function, the Fourier series, the coefficient of a0 will go to 0. Now what about an? We know it's 1 over L, integral from negative L to L, f of x times cosine of n pi x over L. So let's check this out. What happens to this function? Well, f of x is odd, right? That's what we're saying if f of x is odd. And we have cosine, that's even. So odd times even. What is odd function times an even function? Odd times even, is it? No, not numbers. We're talking about functions. So think of it this way. So take x cubed, that's an odd function, even function x squared, right? If you multiply them, what happens? It's odd, right? Yeah, so you get the integral of negative L to L of an odd function. So now you're integrating really an odd function on a symmetric interval. So what happened to this coefficient? So we're integrating odd function on a symmetric interval. This is also 0, right? That's what we said earlier. So hence, what can we say? We say that if f of x is odd, then it only has Fourier sign representation, right? So in terms of the formula, we would say f of x is only equal to the sum n equals 1 to infinity bn sine of n pi x over L. So that will be your Fourier series representation if your function is even. So you see how you can save time by just letting a0 to be 0, an to be 0 if the function you're looking at is an odd function. So, and then we'll have same thing for cosine Fourier representation if the function is even. So any questions on this? Does it make sense, kind of, guys? Okay, so just review, see if you can go through some homework questions from 10.2. So we did cover 10.4, most of it. I just need to do more examples with you guys. So I will encourage you to just look at some homework questions, see if this formula makes sense. And these properties are very useful. Like really, if you're integrating an even function, it can cut down so much of calculation when you're computing this coefficient, so that at the end, when you're looking at the Fourier representation of an odd function, you don't have to worry about a0 because it's going to be 0. So if you integrate, you'll be wasting your time because at the end you're going to get 0. Even similarly for an will also go to 0 because eventually the integral will go to 0. So if you know these little details, you can cut down a lot of computation and just jump to computing bn, because bn will survive because you will be integrating an odd function with sine, where sine is also an odd function. So odd function times an odd function give you even function, so it will survive. So bn will survive if f of x is odd. And then same thing for even functions. bn will go to 0, a0 will survive, an will survive. So that way you can always cut down some of the computation for this section. Alright, so this is it for today. I hope you guys enjoyed. I know we went through a lot, but do some examples. Hopefully this will make sense, and then we can continue more on this and do some examples next time and finish up with the heat equation next class. Any questions? Okay. Yeah, I think that's the one with chapter 10 materials. Yeah. All right, any other questions, guys, before we go? Alright, so if there are no questions, you are good to go. I'll put up the video on YouTube and you guys can watch it up later. I will see you all tomorrow. Have a good one, guys.